In this week's lecture, we will discuss capacitance. Okay, so last time we discussed electrostatic potential for different configurations. And so let's go through some of these, like for example, the spherical shell. V is equal to K, Q over R. Okay, shell. Radius R, say, charge Q. Then the second example might be a ring. This is V is equal to K Q square root X squared plus R squared. Radius R, position X there, charge Q in this case as well. This one technically should be over R, R greater than R. Right there. Okay. Now, what you will notice is that V is going to be related to R with some basically stuff, right, out front. So we denote that, we note V is proportional to Q, sorry, all right, with some multiplicative factors. Now these factors are not easy, right? So in this case, this is K over R, and this is K over square root of X squared plus R squared, right? So it's not always easy, but it's just some factors there, right? But it's always multiplied times Q. That's the thing that you should notice here, right? So let me define. We'll define the capacitance C, well, C is equal to Q over V, okay? So what it means is that for a spherical shell, right, C is equal to Q over V, Q over KQ over R, that's 4 pi epsilon naught R. Okay, and then basically we want to do it for a ring. C is equal to Q over V. That's going to be Q over KQ again. Square root of X squared plus R squared. This entire thing is 4 pi epsilon naught square root of X squared plus R squared. All right, so basically you recall where this epsilon naught comes from. Recall K is equal to 1 over 4 pi epsilon naught, right? Okay, so the epsilon naught appears on the top. Part of the reason why epsilon was defined, part of the reason why C is defined this way as well. Okay, so the unit of C is called a farad. Okay, F, all right, which is basically C over V, okay? So you can basically just see right here, this is unit of charge, unit of potential. Potential is basically a volt. Unit charge is a coulomb. So coulomb over volts, basically. Right? Okay. I don't know why it's called a farad. All right. It should be called Faraday, because after Faraday. I don't know why they shortened to farad. All right. Anyway, let's see. So the other issue is that C is a absurdly large unit, kind of like coulomb is an absurdly large unit. Right, so this is why like C's are always terrible. So we typically use farad is a large unit. All right. So we typically use a microfarad, which is 10 to the minus 6 farads, or a picofarad, which is 10 to the minus 12 farads, right? So this is a more typical thing, right? So this is micro, and this is pico. Okay. All right, so capacitors, I mean, like, I wish I could show you what some of these things capacitors are used for, basically. Capacitors, lots of uses. Basically, anything you need to basically store or release charge very quickly, or basically use electronic circuits, so store and release energy. Okay, and also electronics. Okay. So for instance, like using computers or phones and whatnot, and sometimes there are, if you can build really powerful capacitors like these called supercapacitors, you could basically also use them to store and release energy very quickly. Okay, so we're going to go through the classic capacitor, right? And the classic capacitor, parallel plate capacitor. And everything else is more or less derived from the parallel plate capacitor, right? So let's draw what parallel plate capacitor looks like. You have two plates that are parallel to each other. This one might have a charge plus Q. This one might have a charge negative Q. The distance between them is some distance D. The area of each one is area A. I'm going to call this one plate 1, plate 2. And because of the plus charge on this side, the electric field looks like this. It just goes in this direction. All right, so this is the E field. Right. Now, let's go get to what the potential difference is. Right. The potential difference, okay, between plates 1 and 2, right, is, okay, so what is that? It's actually pretty simple. So this is the potential is really V is equal to integral from 1 to 2 of the electric field dotted with dl, right? And technically we have a minus sign here as well, right? So this is just going to be integral. So electric field is going to be along the x direction. It's going to be E dx, 1 and 2, minus sign there. All right. So roughly speaking, this is going to be basically E times D. All right. Okay. Let me see if I want to think about this a little more carefully. Right. If I want to be pedantic about it, okay, this is a plus sign because E is equal to E times minus x hat direction. Okay, so the minus sign will cancel out this minus sign up front. So this will be a plus ED there. All right. Chose it in this way basically so that this thing's nice and positive here. Okay. So what's the electric field then in that case? All right, so we also know for an electric field, E is equal to sigma over epsilon, which is a charge net, charge per unit area. So this is just going to be, what's the charge? Well, that charge is Q. What's the area? The area is A. All right, divided by epsilon 0. Sorry, epsilon 0 here. Okay. So you combine these two things together. It means like V is equal to, let's see, it's E times D, so it's Q over A epsilon 0 times D. Right? And so what this implies is that C is equal to Q over V, right? You could just work this thing out. It turns out to be something to like, if you flip this thing, divide the Q out. Oh, no Q there. It's going to be epsilon 0 A over D. Okay? So that's the first important result we're going to have, right? Okay, so the capacitance here depends on A and D. Okay, so what's interesting about this? A and D tells you it's essentially the geometry of the problem, right? There's certain area, there's certain distance between the plates and stuff like that. It doesn't depend on Q, for instance, the charge release. It just depends on that, right? So what this means, right, is that capacitance depends only on configuration and geometry. Okay, that's all it depends on, right? And so the capacitance encodes the geometry of the object that we're going to study, right? All right. So let's go through some examples of this. All right. And the first thing we'll look at is the cylindrical capacitor. Okay. So let's look at cylindrical capacitor. It looks something like this. Let's draw it out. So we have an inner shell that has some radius R1, say. Okay. I don't know if you can see R1. I'll write R1 here again. R1. Okay. And then there's an outer shell here. R2. And this goes off to or some distance there. Okay. And I want to make this entire thing, I'll draw like this. Okay. This entire thing have some length L and some charge. I'll put a plus Q here on the inner part, minus Q on the outer part. Okay. Okay, so I want to determine the capacitance of this capacitor, cylindrical capacitor. All right. So how do I do that? I want to systematically do it. All right. So generally speaking, a lot of times what we're going to basically use, you have to basically figure out what the electric field is, what the potential is, and then figure out what capacitance is. Right. Okay. Sometimes you might know what the potential is a priori. All right. But most of the time you won't. All right. Because most of the time they'll involve like funny geometries or something like that, which is like you just have to figure out what the electric field has to be first, right? So there's a three-step process. for finding C. Okay, first 1, 2, 3. Okay, so the first one is to find an E field. Okay, the second one is find V is equal to integral of dl dot with E minus sign technically. Generally, you could ignore the sign, right? Because it's just gonna work out. Inevitably, what you want to do, if you're very careful, is you want to make sure V is positive, right? So, because capacitance C is a positive term. And finally, let C is equal to Q over V. All right, so that's the three-step process for it. So I'm apply this three-step process to the cylindrical capacitor right now. Okay, so let's go ahead and do that. The first thing we'll do is find the electric field. Okay, so for the cylindrical capacitor, we're going to do 1, find electric field. Okay. Now, what we're interested in, all right, is basically what the potential is between these two shells, right? Right. So we're going to look at the potential difference between those two shells, right? Okay. So what we care about is we'll just find field, and then we'll be careful. Okay, we are only interested in E field between the two shells. Okay, so that means I care about basically R1 less than R less than R2. Okay, that's what I care about. Right, so let's keep in mind this picture here. R1 is the inner radius, R2 is the outer radius. Okay, good. So how do I figure this out? Well, it's a classic thing. Okay, how do we find it? Use Gauss's law. I'm going to redraw the picture here, just so that we have a good working understanding how this thing looks like. Okay, and this is going to be R1, that's R2, okay. This is L, say, all right. And in order to figure out the E field, we use Gauss's law. Let's write it down first. It's going to be basically E times A is equal to, or technically it's E dot dA integrate over some surface, which is going to be E times A. Because if it's not E times A, it's too hard to figure out. Okay, so it's equal to Q inside over epsilon naught. Okay, so this is I believe this was plus Q, and this was minus Q. All right. Okay, so I need to figure out what this electric field looks like. All right, let's go ahead and figure this out very carefully. All right, so I got to figure out my Gaussian surface. My Gaussian surface is going to be something that looks like this, like a little cylinder between the two. Some R. Okay, that's going to be some distance there. All right, so what's the area here? Well, it's a usual story now, right? So, for instance, like what we have to note is that basically the electric field is going to be pointing outward here at every point, okay? Because if I spin this around, I can't have electric field which is pointing along the cylinder because they will map into each other, right? So I have to basically pointing outward like this, right? And so what I get is that basically electric field is going to be along the r hat direction, right? And so the only area I care about is this area here. I don't have to carry all the caps. I just care about the area of the cylinder part. So what's the area of that cylinder part? Well, it's just some length. So E times L times the width is basically the circumference of this circle, 2 pi r is equal to Q inside. There's a Sometimes it's a hard part. In this case, it's the easy part. What's the charge contained inside the cylinder? Well, it doesn't contain the negative Q part. It just contains the positive Q part. So it's just basically plus Q divided by epsilon naught. There, okay? I'm done. All right, so let's go ahead and basically work this thing out. That implies that this is equal to the E field is equal to Q over 2 pi RL epsilon naught, okay? And if I want to be really careful about this, this is a vector that's in the r hat direction, right? R hat is a cylindrical radius. Okay, that's basically part 1 now, okay? Now part 2, find V is equal to integral of dl dot V, okay? Let's go ahead and find that out now. Part 2. V is equal to the integral minus E dot dl, okay? All right. Now, ultimately, I'm going to basically, whatever this, I have a sign here. This is the correct way of defining the potential difference. But ultimately, I care about the positive value. I don't care about what the sign of this thing necessarily. Okay, let's figure it out. So this is going to be integral of, well, this is going to be E is just something here. Right, it's E r hat, right? Because it's in the r hat direction. Dot this with dl. Okay. If you minus this term here is just dr then. Integral of E dr. I'm going from basically shell 1 to shell 2. Right. Okay. So let's go ahead and do this thing now. So this is going to be equal to, all right, this is Q over, okay, 2 pi, I'm taking all the constants out. So 2 pi is a constant, L is a constant, epsilon naught is a constant, integral, don't forget the minus sign, 1 to 2, so it's 1 over R dr, okay? So what is this thing? Well, that's just the logarithm of R, so minus Q over 2 pi L epsilon naught, the logarithm of R evaluated between 2 and 1. Okay? Okay? Let's go ahead and keep going, right? So this is going to equal to, we'll be very pedantic about this, Q over 2 pi L epsilon naught, okay, minus sign here, logarithm of R2 minus logarithm of R1, right? Okay, and then this is going to be equal to minus Q over 2 pi L epsilon naught. This term right here can be written as logarithm of R2 over R1. Okay, logarithm of R2 over R1. All right. Now this thing has an extra minus sign. R2 is bigger than R1, so the logarithm of this thing will be positive. I just care about the positive part. So I'm going to ignore this minus sign, all right? So we will ignore this minus sign. Okay. Okay, so that's number 2 then, okay? So that implies I get basically absolute value of V, which is what I really care about, Q over 2 pi L epsilon naught, logarithm of R2 over R1, okay? So I got part 2. Okay, so that's part 2 of my 3-step process. Part 3 is to find the capacitance. So in part 3 here, I let C equals Q over V. Okay, you can see what's beautiful about this, right? There's the Q right there. I'm going to cancel it out. So Q over 2 pi L epsilon naught, logarithm of R2 over R1. These cancel, and now I'm done. 2 pi L epsilon naught divided by logarithm of R2 over R1. Okay? And there it is, right? I found the capacitance of a cylindrical capacitor. Okay. Right. Okay, so make sure I have everything here. Good. And then this piece right here is perfect. Okay, good. So, all right, so let's keep going, right? Okay, and so basically you can find a few of these things. This is cylindrical capacitor. Next thing you're going to work on is like the spherical capacitor. It's very similar, so it's not particularly difficult. Okay, so let's discuss basically some of the what we referred to earlier. So capacitors are useful for storing electrical energy. Okay. So in particular, right, recall U, right, the electrostatic energy is the integral of du, right? And what is that? That's the integral of V dq, right? Well, this is the potential, right? Because remember, okay, so you integrate over all the potential, you get that, okay? Now, what is interesting about this, the potential, okay, because C is equal to Q over V, that means that V is equal to Q over C, all right? So let's look again now. So the integral of Q over C dq, okay? Now C, like I referred to earlier, is generally depends on geometry. Only on geometry, not Q. And so you get something very nice here. And I'm getting something that looks like this. U is equal to 1/2. So this is integral of 0 to Q. Say 0 to Q. 1/2 Q squared over C. Okay? Right? Well, what is this also equal to? So basically, remember, this is also V, so this is 1/2 VQ, right? And then similarly, this is also, we can also rewrite this as 1/2 CV squared. Okay? So there's 3 different ways of writing it, all right? So this was basically same as before. And these 2 things are new ways of writing this thing, right, in terms of capacitance, right? So what we have is that capacitance, the capacitance is related to the amount of stored energy, right? Okay, so let's go ahead and do this now. Okay. So to basically show this more explicitly, all right, so let's look at the parallel plate capacitor again. All right, so here's my parallel plate capacitor. This is a plus Q, the minus Q here. There's some area here associated with this thing. Area A between these two, all right? And I know the electric field is equal to sigma over epsilon naught, which is Q over A epsilon naught. All right, so that's the electric field between the two. And if I take these two things and I bring them out to infinity and bring them back, all right, the amount of work, or the other way to think about it is, imagine I take these two plates and put them right next to each other, okay? And so basically when they're right next to each other, their total charge is 0, and so there's this basically the same as free space. And I slowly just pull them apart, okay? So how much work does need to be done in that case? Well, the amount of work needed to pull these two plates apart is the integral of the force times the distance, right? And so this is going to be equal to, well, this is some Q times E, all right, times the dl. E is a constant, right, along basically this x direction. And so this is going to be basically going to be Q times A epsilon naught times integral dl is just the distance I pull them apart. Let's say I pull them apart some distance d. And so this is going to be equal to Q squared over A epsilon naught times d. And then you'll recognize that this thing right here is essentially 1 over c. So it's basically Q squared over c. All right? Okay. Now, what you will notice here, this is something slightly interesting here, okay, is that this value is 2x, the electrostatic energy two times the electrostatic energy that I got from above. Right? So basically what I should have gotten is basically 1/2 Q squared over C, but I got actually like Q squared over C, right? So that's 2 times that energy, right? Right, and let's see, and there's a reason for this, right? Okay, so the reason for this is that if I ask, okay, so the reason for this is that before, up here, what I'm doing is I'm essentially assembling charges from infinity. So above, I assemble charges from infinity. Okay? That's where this part comes from, right? Integral up to Q. So you take the charges, bring from Q, you have two places separated, right? You slowly put the charges in and you basically generate this charge, right? In that case, you get the electrostatic energy of this is 1/2, right? Okay? So then, in this case, I took two plates, I put them right there, and I pull them apart. I got basically q squared. Now, there should be no difference between these two, right? Now, the reason is that there's one more piece of energy I'm storing somewhere, which I did not account for. Here, I just got basically electrostatic energy associated with the capacitor, with the two plates apart from each other. But there's one other piece which I have missed earlier, okay? Okay, so let's go ahead and discuss this piece, okay? Okay, so one thing I will note is the following, okay? So I'm going to look at this way of writing it, okay? So U is equal to 1/2 CV squared, okay? Well, what's the way of writing CV squared? Well, CV is just electrostatic energy, electric field times D. So it's basically 1/2 C E squared D squared for this parallel plate here, okay? And so what we have is 1/2, what's C now is epsilon naught A over D E squared D squared, okay? Okay, so let's go kill this thing, kill that. A times D is the volume, right? So it's 1/2 epsilon 0 E squared times the volume, right? And what's interesting about this, right? This is energy. This has units of energy, okay? This has units of volume here, okay? Which means 1/2 epsilon E squared has units of energy divided by volume, or energy density, okay? So then what we have is, that means that little u, right, is equal to 1/2 epsilon naught E squared is the energy density of the electric field. Okay? So that's the answer, right? That's where the second half comes from. The first half comes from the fact that there's a charge and there's a potential difference between these two. Okay? That's the first piece of it. The second piece comes from the fact that as you build this charge up from infinity, you also build up the electric field between them, and electric field also has energy associated with it. And it's basically 1/2 of the total energy. So you combine the two, 1/2 plus 1/2, you get basically 1. So that's the difference here, right? So in this case, when I put them together and I slowly pull them apart, as I did that, I basically put energy into the electric field and into the potential difference between the two charges, right? So that's why I got this basically factor 2 here as well, right? So if you count for all the energy, you get basically this factor 2 out as well, right? So now, what you can do is that basically, in general, well, U, which is going to be the electrostatic potential energy, is going to be integral of U dV, right? Where this is the energy density of electric field. All right, and U is going to be equal to 1/2 epsilon naught E squared, just generally, okay? All right, so now you can basically use this to figure out the electrostatic potential energy of various configurations. So we can use this to find electrostatic potential energy of various configurations. Okay, so let's do one of them. So let's do basically a spherical shell. That's one shell here. This will be plus Q. Another shell here. This will be minus Q. Okay. and I'm going to basically call this RA, and that's going to be RB. Okay, and I know what the electric field between these regions are. Electric field is pretty simple, right? This is just going to be KQ over R squared R hat. Okay, that's my electric field between the two between the two shells, right? Okay, so U is equal to what? So I'm going to find capital U, right? So what U is equal to? U is equal to, well, this is 1/2 epsilon naught E squared, right? So that's 1/2 epsilon naught. So this is going to be basically be equal to K squared Q squared over R squared. All right. And so if I write this thing out, so the epsilon is related to K by 1 over 4 pi K. So it kills a one factor K, so it's going to be equal to 1 over 8 pi K Q squared over, R to the 4th now. All right. Okay. So then U is equal to integral of U dV, as stated earlier. That's going to be equal to, okay, 1 over 8 pi, put everything here now, K Q squared over R to the 4th times the area 4 pi R squared R with R squared dr. All right. Okay, let's go ahead and figure this thing out. That kills that, makes it a 2. This kills that, makes that 2 there. All right. And so it's going to be equal to, okay, there's a 1/2 there. All right. There's going to be a integral KQ squared over R squared dr. Okay, so that pulls that minus sign. Oops. 1/2 of minus sign KQ over R, evaluated at R equals RA to RB. Right, and this will work out. Okay, and so this is going to be equal to 1/2. I'll flip the sign of these things. KQ 1 over RA minus 1 over RA, sorry, 1 over RB. Okay, beautiful, right? And so basically, if we take this R and set this to infinity, right, as RB goes to infinity, all right, we get U of the sphere, right, 1/2 KQ over R, right, which is exactly what we got before, okay, beautiful. All right, now I want to discuss something about the second thing these were used for, which is in circuits. All right. Okay, so let's talk about capacitors in circuits. Okay, so let's look at how capacitors behave in circuits, right? Right? Okay, so in order to do that, we're going to have to learn how to read a circuit first, all right? So let me just draw a picture out how this thing looks, okay? So there are two ways of connecting stuff in circuits, all right? So two ways of connecting. The first way of connecting is that suppose you have basically an object like this. call it just round things. We don't know what these round things do exactly. You connect them like this, or you can connect them like this, all right? Okay, so this is called series. Why? You're lining them up together, so electric flows through one, then flows the other. And then you also connect like this one, which is parallel. Okay, the electricity can choose to basically flow in one or the other case, right? And what I'm going to do here is I'm going to connect a voltmeter here. A voltmeter has these thin wires and a V between the two, right? This is a little voltmeter. Right, usually one word or two words. Okay, and you get several different ways. So suppose I connect the voltmeter in this way. Okay, there are two ways of a voltmeter. So in one case, I'm going to connect the voltmeter across this one, across each one of these circuit elements, V1. And then the second circuit element, V2. Okay, and then similarly, I do the same thing here. So I'll connect basically V1 in this case, V1, and then I'll connect basically V2 here, right? So along the wire, okay, if the wires are connected to each other, they all have the same voltages, right? So what that means is that basically along this one, this connects along to this wire. These wires are all connected, there's nothing in between them. And so what you get is that V is equal to V1 is equal to V2. Okay, so that's the classic case of a parallel circuit. On this hand, on the other hand, basically the voltages, this wire is not connected; they're just connected to each other. Right, so these things will reach the same voltages, right? But the potential drop will be different between these two. So in this case, V is equal to V1 plus V2. Right, the potential drop across the entire thing has to be the same. Right, so that's the key difference basically between these two. Right? Okay. So let's basically take a look at this thing. All right. So let's imagine. Let's put some capacitors in. Okay. So let's draw this thing out first. We're going to draw it as a parallel one first. Okay. We'll do a series one later. So let's draw a parallel one. So there it is. There it is. I'll put my capacitor there. The capacitor is basically denoted by two straight lines. Okay. Okay. Right. Okay. And I'm going to just dump some charge in this thing. So there's going to be some charge in this one. So basically, pour some current in here. There's going to be some charge here. It's going to be Q1. There can be the negative version of this, minus Q1. It's going to be basically Q2 here, minus Q2. And these are two different capacitors. It's going to be C1 and it's going to be C2. All right? Okay. Now, this will be equivalent to a capacitor which has some C effective, which I do not know yet, okay? Right? So if I wire this thing up, some voltmeter across this entire thing, all right? Of course, you realize that if I do this same thing, this is V2, V1, okay? This I will get basically V1 is equal to V2, right? Equals V, okay? Likewise, I wire this thing up as well. That's V. This is some V. These V's have to be equal to each other, because that's what this equivalent capacitance is going to be. The other thing I know is that the total charge on these capacitors is going to be some charge Q, and Q is going to be equal to Q1 plus Q2, right? Because basically I take these two charges, I dump them all in the same capacitor, I get some equivalent capacitors, right? The way to think about this is that you have these capacitors in parallel. Suppose you want to manufacture, you want to say, hey, I don't want two capacitors, I can just buy one. What's the effective capacitance I have to basically get in order to place two capacitors that has the same properties? Okay. Okay, so what do we know? We know this is true, okay? We also know that basically C1 V1 equals to Q1, C2 V2 is equal to Q2, right? And Q is equal to Q1 plus Q2, right? So let's find the effective capacitance, right? So effective capacitance is C effective, right? And what's C effective? Well, C effective is equal to Q over V, right? And this is going to be equal to Q1 plus Q2 over V. Well, I do know what Q1 is. It's going to be this one right here. So it's going to be C1 V1 plus C2 V2 over V. But V1 and V2 are all V. So this can be also equal to C1 plus C2 V over V. The V's cancel out. And so you're left with the C effective is equal to C1 plus C2, okay? So that's the first rule, right? You can sum up the capacitance of stuff in parallel, right? So to basically drive this point home, right, we're going to consider a series of three capacitors that are in parallel. C1, C2, C3, hook them up together, okay, that's hooked up, right, okay, and again, basically, Q1 is equal to C1V, okay, 1, which is C1V, okay, Q2 is equal to C2V2, which is C2V, and then Q3, you can guess this is going to be C3V, right? Okay, and Q total is equal to Q1 plus Q2 plus Q3, all right? And so C effective is equal to Q total over V, which is just going to, you work this all out, C1 plus C2 plus C3, right? So what that means that in parallel, C effective is equal to C1 plus C2 plus C3 plus dot 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 dot, okay? So you just add the capacitance up to get the effective capacitance of capacitors that are wired in parallel. Okay. So now let's consider the next one, now in series. All right. I'm going to draw this one out. Okay, here's my C1, C2, C3. Okay, and attach a voltmeter to everything, and then little voltmeters to each one of them. This will be V1, V2, V3. Okay. Okay, beautiful. So I got all that. All right. Now, what do I know? Okay, so I'm gonna pump some stuff in this one. I'm gonna basically make this plus Q. This has to be minus Q. Now, because it's minus Q, I have to put plus Q here again. Minus Q, plus Q, minus Q. All right. Okay, so the entire thing has basically a plus Q and minus Q at the bottom. Right. Okay. So now what this means, Q1 equals Q2 equals Q3 equals Q, all right? Right? And then likewise, basically, if I want to figure out what V1 is, V1 is equal to Q1 over C1, it's just Q over C1, right? V2 is equal to Q over C2, and V3 is equal to Q over C3, right? Right, so I'm dropping the fact that like I'm going from 1 to 2 because all the Q's are the same, right? Okay, so what I know is that I can replace this with some effective thing, right? That has some charge Q, minus Q here, and has some potential drop, which is the same as what I have in this case. So what do I know? Well, in series, V is equal to V1 plus V2 plus V3, okay? This here is going to be V is equal to Q over C effective, all right? So this is also going to be Q over C effective, right? And I know what these things are. That's just basically these Q here. So it's going to equal to Q over C1, Q over C2, Q over C3 equals Q over C effective. Now I'm done. These things cancel, become 1s. And so you get basically 1 over C effective is equal to 1 over C1 plus 1 over C2 plus 1 over C3, right? Plus dot 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 in principle if you wire more of these things in series, right? So to summarize, in series, 1 over C effective equals 1 over C1 plus 1 over C2 plus 1 over C3 plus dot 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 dot. And in parallel, C effective is equal to C1 plus C2 plus C3 plus dot 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 dot. Okay? All right. So that's basically capacitors in a circuit. All right. Okay. Now, in this last bit, I'm going to discuss dielectrics. All right. So generally, when we discuss capacitors up to this point, we just assume there was nothing between the plates, right? That's generally not true. Generally, you put something between the plates, right? And this material is called a dielectric. All right, so let's discuss this. Right? Dielectrics, right? And they're important because they change the properties of a capacitor, right? So what's a dielectric? So a dielectric is, okay, so when an insulating material is placed between the plates of a capacitor, okay, the capacitance increases, right? Doesn't decrease, always increases, right? So this material is called a dielectric, right? So general statement, all materials are dielectric, so it's just that some things are better than others, okay? So they work by weakening the E field, which lowers V for given Q. So you have some Q, right? It works by lowering it, okay? Okay, and so the amount okay, depends on material. And is given by kappa, like a K, Greek K, okay, which is known as the dielectric constant. And this varies from material to material. So let's draw a little plot. Okay, this is kappa, this is material, right? And so a few materials, so for air, gasoline, You might want more gasoline. I'll tell you why in a second. Paper. Paper is a very common one, and ceramic. Okay. For any of you who ever built a desktop computer before, occasionally you might buy a motherboard that says like ceramic capacitors. This is why. Okay. All right. So what's kappa? So kappa is 1 for air. It's 2 for gasoline. It's about 4 for paper and 7 for ceramic. Okay. And what happens is that I said it lowers the E field. So E, the electric field, goes to E, which is E0, which is electric field in the vacuum divided by kappa. All right. All right. So this is E field for nothing between. Right? So for air, it's the same as almost nothing. It's actually a little above 1, so it lowers it just a tiny, tiny, tiny bit. Okay. But for gasoline, it lowers the electric field by a factor 2, paper lowered by a factor 4, and ceramic lowered by a factor 7. Substantial decreases in it. Right? Okay. And so basically, for a parallel plate capacitor, right, V is equal to ED, right, which means that this becomes V is equal to E0 D, right, over kappa, okay, which is V0 over kappa. So it lowers the potential by an equivalent amount. And then likewise, C is Q over V. This is Q over V0 divided by kappa. So it's going to be equal to kappa Q over V0, which is kappa C0. So this is basically capacitance for nothing between. Okay? All right. So let's see what I want to say about this. Okay. Now, up to this point, we basically wrote everything in terms of epsilon 0, okay? And there's a reason for that, right? It's basically related to this capacity. You notice I hope E0, V0, C0. So basically, in a dielectric, okay, epsilon 0 goes to epsilon, which is just kappa times epsilon 0. So now these have definitions. This is called permittivity. And this is the permittivity of a vacuum, but has we formally call it permittivity of free space. Okay? So that's basically it. So anywhere you see in a dielectric, you can replace literally epsilon 0 with epsilon, the permittivity, and then get the right answer, as long as you know the scale. Okay. So let's talk a little bit about how these things work exactly. All right? So how do they work on a molecular basis? So what happens is that if you look at, like, let's say a water molecule, for instance. What's a water molecule? So say water. It's basically H2O, right? So you have an oxygen atom here connected with 2 hydrogen atoms, right? And this angle is almost 90 degrees. It's actually a little larger than 90 degrees, but it's almost 90 degrees or so, right? So what happens is that electrons are bounded more strongly to the oxygen atom, so that makes this slightly negative, and less strongly to the hydrogen atoms, which makes this slightly positive, right? So what that means is that this has a dipole moment. Okay? This is the intrinsic dipole moment of a water molecule. And there are lots of molecules which have this sort of feature. Even if they don't have this feature, if you apply electric field across them, it can induce a dipole moment across it, which will act the same way. Okay? So what happens is that in the presence of electric field, right? Okay, molecules will start to align. Okay, so for instance, basically, if you think about this thing, then you think of this thing as basically an elongated object with a negative charge and a positive charge here. You apply electric field across that material now. Okay, this will start to line them up. So it'll be negative here, positive here, negative here, positive, negative, positive, negative, positive, negative, positive, negative, positive, right? So if you put this into, let's say, a parallel capacitor here, this is the material between it, these are two plates, that's my material here, okay? What you're going to end up getting is that there's going to be some negative charge on here, some net negative charge, some net positive charge here, right? So as electric field comes in, some of it gets canceled out, right? So you get basically fewer charges that go across. Okay, so that weakens the electric field. So for kappa equals 2, right? E field is reduced by 2. Okay, whoops, by 2, right? And likewise, this applies to everything else as well, right? So this charge right here, these charges right here, are called the bound charges. Why? Because they're bound, but they are a charge, right? Okay. And this piece out here, these are the free charges. Okay. So what that means is that there's electric field out here, which is the free electric field, and electric field out inside the electric, which is the bound electric field, right? So the electric field of the free part, well, actually it's going to be sigma the free part divided by epsilon 0, okay? And the electric field of the bound part, that's sigma of the bound part times epsilon 0, okay? And what I know is that, there's some electric field here, right? There's some effective bound electric field which helps cancel it, okay? And also what I know is that E field inside is equal to the electric field of the free part minus electric field of the bound part, and that's going to be equal to basically electric field of the free part over kappa. That's the material, that's the amount of reduction electric field I have to have, right? Okay, so what that means is that electric field of the bound part is going to be equal to, well, we'll see, so this is true here, so bring this one side, bring this electric field of the free part times 1 minus 1 over kappa. Okay, that's from this equation right there, right? Okay, and so if I apply these two together, that means the surface charge density, sigma bound, is just going to be equal to, because this is true here now, that's true there, this is sigma free times 1 minus 1 over kappa. Okay? Now, so if you have basically kappa equals 1, let's say for air or vacuum, right? that means that sigma bound is equal to, well, 1 minus 1 over 1 is 1, 0. Okay? Right. Now, why is this useful ultimately? So this is the last piece I want to talk about today. Why is it useful? Well, one thing it's useful for is you can basically, if you measure voltages, all right, you can come up with a way of measuring, let's say, different levels of stuff, right? So let's show how this is useful. Okay. All right. So let's imagine I have the following. Okay. So I have, let's say, and the reason why I talk about gas, so you have a gas tank here in your car. And I'm going to put inside this thing is a cylindrical capacitor. Plunge the cylindrical capacitor in this gas tank. Okay. There's my cylindrical capacitor. This has basically R1, R2, all right, has some length L, say, all right, and this gas tank is like full of some gas, right? I don't know what the gas is, it's full of some gas, right? And the distance, basically this distance here is X, okay? All right, so what I want to do is I want to just figure out basically, can I figure out what X is, the level of the gas, based on the capacitance of this total capacitor, right? So this will have some capacitance C1 up here, some kind of C2 down there, and the basic difference between these two is the fact that this one has some gas in it, which is serves as some dielectric constant, right? Okay, so let's find the capacitance. Find capacitance, right? And again, it's a three-step process, right? So first step, find E field, like we discussed just earlier. Second step process, find V is equal to integral of E dot dl. Okay, find the magnitude of this thing. 3, C is equal to Q over V. All right. Okay. So part A. So 1. Okay, this is going to be E times A is equal to Q inside over epsilon naught, right? Well, what's that going to do? So I don't necessarily know what Q inside, but I do probably know there's some surface charge sigma 1 there, all right? Okay, along this thing. And so this is going to be equal to, let me get this right now, E times A, okay, I'm going to write this as 2 pi R, okay, times some distance L, right? And this L is going to vary, actually, so this is going to vary later. I'm going to just find the general form first. Equals sigma inside. What's sigma inside? Well, that's just going to be some sigma 1, all right, or sigma. I'll write as sigma. This will vary again, all right, times 2 pi R1 times L, right? Because I just care about this radius here. That's the sigma I care about. Divide by, says Q inside, divide by epsilon naught, all right? And so the 2 pi's will kill each other, right? The L's will kill each other as well. And so you get something very simple. E is equal to sigma R1 over R times epsilon naught. That's right. Yep. Perfect. Okay. Good. Okay, so that's basically the first thing. All right. Now, what I'm going to do, now that I have this term here, all right, is I'm going to find V now. Okay, so number 2. Okay, okay, v is equal to minus integral of e dl, right? Okay, this is all in the r hat direction. This one would just be dr, so it'd be integral of e dr. I'm dropping the minus sign here because I feel like it, all right? Also, I know it's not going to matter at the end of the day because I take the absolute value of it anyway. So this is just going to be, let's see, this is going to be sigma r1 over epsilon naught integral of 1 over r dr, integral from 1 to 2, okay? So this is just going to be sigma r1 over epsilon naught, and then this is going to be the logarithm of r2 over r1, right? Good. That's number 2. Number 3, find c. C is equal to q over v. So this is just going to be equal to q, which is slightly annoying. That's going to be q, I just figure out here, is 2 pi r1 L times sigma. So it's 2 pi r1 L times sigma, right? Divided by this one, sigma r1 over epsilon naught log of r2 over r1, okay? This will kill that, that will kill that, right? So this is just going to be equal to epsilon naught 2 pi epsilon naught L over logarithm r2 over r1, okay? All right, so let's take a breather here for just a second, all right? What I will notice, all right, is that this L was free. I could be free anything on. The sigmas, which I was so worried about earlier, just vanish. Don't care about sigmas there. So I just need a capacitance meter between these things. I can measure the capacitance of this thing, all right? And this depends on two things. It depends on epsilon 0 and L. And as I mentioned before, to get it for a dielectric, you literally replace epsilon 0 with epsilon, which is epsilon 0 divided by kappa, okay? Okay, or kappa times epsilon 0. Make sure I get it right. Right, okay, perfect. Okay, so as I mentioned earlier, basically we're gonna replace everything with epsilon here, right? So let's do that. This is going to be equal to 2 pi epsilon L over logarithm r2 over r1. Now, this is the same r2 over r1 for top and bottom, so I don't really care about that. This L will change, right? So, there are two capacitors here. They're wired essentially in parallel, right? So the total capacitance is going to be equal to C1 plus C2, right? And what's C1? Well, let's write this thing. So this is C1. That's going to be 2 pi, okay? This is air up here, okay? Gas down here, okay? So I'll write this as epsilon air, okay? Times little l. Little l is this piece right here. That's going to be L times minus x, L minus x, okay? Divided by logarithm r2 over r1. This is the same as before, okay? Plus now 2 pi, this C2, that's going to be epsilon gas, right, the gasoline part, times x now, that's this length right here, divided by logarithm r2 over r1, okay? Okay, so I stare at this thing. I'm going to basically write this thing out now, all right? So epsilon air is just basically kappa is 1, so it's just basically going to be 2 pi epsilon 0 L minus x over the logarithm r2 over r1 plus now, this is basically 2 pi, this would be kappa epsilon 0, kappa in this case is 2, but I'm not going to worry about the exact value right now, logarithm r2 over r1, okay? Right. Now, one thing I will notice is that if it's empty, C empty, right, that means x is 0 in that case. That should be 2 pi epsilon 0 L over logarithm R2 over R1, right? And now basically I'm going to construct, I'm going to divide C divided by C empty, okay? So I'm going to define C over C empty, okay? So you can see a lot of stuff is going to cancel out now, right? This is going to cancel out this thing, is going to cancel out this thing, the 2 pi's will cancel out this thing, the epsilon will cancel the epsilon zeros out. So if we write this thing out, it looks something like this. This is going to be equal to 1 minus x over L plus kappa x over L, right? And so that means that kappa minus 1 x over L is equal to 1 minus C over C empty, okay? This is something I can measure beforehand, right? I empty the gas tank, I know what C empty is. This is something I'm measuring basically as I'm rolling along, basically in my car, right? And so I can compute what x has to be now, x over L, which, what's x over L? X over L is the amount of fuel left in the car, the fuel fraction car is a half or 1 or whatnot, basically. This is equal to 1 minus C over C empty divided by kappa minus 1. Okay? Right? So by measuring the capacitance here, knowing what this is, knowing what the material is going to be, I can tell you exactly how full my gas tank is going to be. Right? So that's basically one useful application of dielectrics. All right, so that's it for today. Next time we will discuss basically more fascinating facts about electricity and magnetism.